Thetas are just like constants. So when I integrate with respect to r, got 0 to 2 pi. Okay, the antiderivative of this with respect to r is 1/4 r to the 4th cosine theta. Antiderivative of this is 1/4 r to the 4th cosine theta sine theta. And then plus 5/3 r cubed. It probably is. I'm really not even paying attention up here. What is it? 1/4 cosine square. I'm missing the square. Okay, and then that's 1/4. Yeah, that's it. Evaluating from r is 2 to 3. d theta. So you get to plug in 3 for r, and then you get to plug in 2 for r, and then you're going to get a bunch of numbers, right? And it's going to be your life, okay? And that can be done. It's the next integration that's going to be a little bit of work, all right? So I'm just going to talk about the next integration, because you should see at this point that you're really just going to have a bunch of constants in front of these trig functions. So how do you integrate cosine squared? Power reducing formula. This one, probably you could either turn it into the identity, or you could do just let that be u and there's du, you know? This one, well, we won't talk about that. All right, so this is doable. What if this was cosine to the 4th?
You'd have to do
Power reducing twice or something like that. What if this was cosine cubed? You could pull out a cosine and then turn that cosine squared into 1 minus sine squared. And yeah, these were all methods that were covered in trig integrals in Cal 2. I just have a feeling that's going to come up in your take home. Maybe not. Maybe not. Maybe not. No, I think I trimmed this down. It was like 6 problems. I trimmed it down. So, but there are definitely some homework problems that are like this, where you have lots of cosine stuff going on and sine stuff. All right, we're done with that one. Is that okay? Let me see if I have the answer here. Oh, well, there's the object. There it is. Okay. And I had all the stuff in here too, so you could see all the cylinder, the 2 cylinders and the plane cutting through. But I think my drawing was better, don't you? Yeah, I liked mine better. Yeah, there's the integral. So I had the computer do it. And it comes out to 65 pi over 4. Find the volume of the solid between the 2 cylinders, which also lies within the sphere. I was trying not to show that to you already, but I've kind of given it away. You've got a sphere, and you've got 2 cylinders, and you're trying to find the solid between them. So it's this solid right here. So notice that that's between 2 cylinders. So there's your Twizzler looking thing, right? The difference is that the top cap of this thing is being shaved off by the sphere, and the bottom half is being shaved off by a sphere.
Aren't they symmetrical, so you can just...
They are symmetric, yes.
So you can cut it in half?
As long as they're asking for the volume, and they are, right?
Yeah.
So we could just do
The top half?
like the top half of this and double the answer. But we do need to understand, just to start, that we're going to do a triple integral over e of 1 dv, right? That's what we're going to do this problem. Because that's how we get volumes. We can use this triple integral. All right, let's see if we can't get our heads around this. If we were going to do this and double the answer, so cut this off on the ground, cut that off, and then just look the top half only, right? Just that top piece.
Yeah,
if we're just going to do that,
One of your z restrictions would be 0.
the bottom restriction here would be z is 0. And what's the top restriction then?
It would be the square root of x squared squared.
It's the sphere
Well, yeah,
equation
Sphere equation.
or the cylinder equations? Which one of these? It's the sphere equation solved for z. So if I take that sphere equation and solve it for z, it'll be z is equal to the square root of 36 minus x squared minus y squared. I believe that's what it was. Yeah, if you solve that for z, right? Am I moving too fast through this, or are y'all good? You're good? What about the shadow on the ground?
You would have your theta and your R restrictions.
Can you tell me my theta and r restrictions?
Theta is
0 to 2 pi, because I'm going to go all the way around again.
I don't know what the R is.
The r's, well, let's look at our cylinders. It was radius 2 and 4. So my radius is going to go between 2 and 4. And what about my z's? 0 and square root of 36 minus r squared. R squared. Y'all know where we got that, right? Right? Factor out that negative, and you get x squared plus y squared, which is r squared. We did that in polar, so just that makes it a lot easier to work with. With me on that? Okay. So our triple integral would look like, I think I can do this all right here. 0 to 2 pi, 2 to 4, 0 to square root of 36 minus r squared. I'm integrating 1. R, because I'm in cylindrical, dz, dr, d theta, times 2, because I'm going to need to double it. That was only the top half.
So for volume, is it always going to be 1 unless we're given a function?
That's right. If somebody, yes, if you're ever going to use a triple integral to get volume, you need to use a 1 here. Yeah?
Unless otherwise the volume of this function.
Well, if we're integrating anything other than a constant, we're starting to get like density and things like that, right? Or mass.
Yeah, if we're doing a triple integral with something other than 1 here, then we're doing something like a mass calculation or something that we can't really quantify.
So anything other than a constant is just
Anything other than 1
okay.
is 1 is the only thing that's going to give you the volume of that solid.
Okay.
The reason why I'm saying I'm hesitant because we can calculate volumes of solids with double integrals. We did it before. We said, okay, you have a surface here. What's the volume between them? We did that with a double integral. We did. We didn't use a triple for it. But if you do a triple integral over 1, then that's same. You get the same result. The best part of this, though, is that you can use polar cylindrical coordinates. And then as we're about to see, we can use spherical coordinates, which is next. Oh, man, we're doing good on time. There's the computer's calculation of that. I did mine a little different. I did not double it and go from 0 to the top. What I did instead is I went from the bottom of the sphere to the top of the sphere. And to do the bottom, remember when you solve for z, you have plus or minus when you take the square root. If you let the positive root part be on top and the negative root part be on the bottom, then that gives you your top and bottom of the sphere.
Yeah.
So if you do that, you should get an answer of about 383.595. I'm not suggesting you go do it. I wanted to get a numerical answer. Yes?
That's how you would figure it out if, like, let's say the two cylinders weren't directly in the center of the circle.
If the two cylinders were not directly in the center of the sphere, then what? What are you asking?
Like, is that how you would figure out the volume of the two cylinders? Like, that's within the sphere? Because you would have two different...
Oh, you're saying using the top and bottom?
Yeah, because you have two different functions, wouldn't you?
It would still, it depends on how you would be orienting those cylinders. If they're straight up and down, then it would still just double the volume. I just did it this way. I don't know why. I just did.
But like, let's say if it wasn't a cylinder, what if it was a cone?
Yes, then you couldn't do it. You would have to look at the object. I'm not a big fan of using symmetry because it's dangerous. Like if you don't truly know what's going on, like symmetry can get you in trouble.
Like we can only double it because we're integrating to 1.
the only reason we can double is because our region itself, E, is symmetric, and the fact that we're trying to find its volume, right? I mean, that's,
If we're integrating other than just one.
then you can't do it. 3 problems.
Yeah, they probably take all of
Now, those didn't take us that long. I didn't calculate them though, right? Yeah, all the homework problems, they expect you to work them all out. So my video, I should work them all out.
Is there an advantage, or is there a way to know, because I mean, some of this stuff seems similar to the double table, so when you decide to use the double?
That's a great question. Let's take a step back for a second. Let's say that we're trying to do that sphere, okay? Let's say we're trying to find something a little bit easier. Let's just do the top half of a sphere like this. Let's say that that's x squared plus y squared plus z squared equals 36, okay? So that's a sphere of radius 9. And let's say we're looking just above the xy plane, right? And we want the volume of that, all right? Okay, how could I do this with the double integral? With the double integral, what would it be? So what's your shadow on the ground look like? A solid, right? Disk?
Yeah.
So your region on the ground would be this. The radius would be 9. It would be everything in there, right? That's the shadow on the ground? 6, yeah. That's it. Thank you. Did I say 9? And right?
Yeah, you say
It is definitely Monday. Okay, so if I did this with a double integral, it would be integral. I'm going to go to polar, right? So 0 to 2 pi, 0 to 6, and then it's going to be the top thing, right, minus the bottom one. That goes in here. So what would the top function be? This solved for z, right? So that would be square root of 36 minus r squared again, because we could change the x squared plus y squared to r squared. So that would be that, right? That's my top one minus the bottom one. What's the bottom one? 0, right? And then I would have to include in this what? R and then dr d theta, right? That's what I would do. Yes? Okay, now if you do a triple integral instead, you're still going to do 0 to 2 pi. You're still going to go 0 to 6. But now this part's going to be what? 0, the bottom to the top. What was the top? Root 36 minus r squared. And what are you integrating? 1 d r, sorry, r d z d r d theta. When you take your first antiderivative with respect to z, you get z here, don't you? And then you plug in this and this. And when you plug in this for z and then this for z, don't you get this?
Yes.
You get the exact same integral. Now you're back at this. The advantage to triple integrals is that you can do more with triple integrals than you can with double integrals. There's some regions you cannot get using a double integral. You have to use a triple. I don't know if that answers your question. Okay. All right. Let's move on. And for this one, we're gonna switch to our last coordinate system, spherical. And as the name implies, if you move around in this system, this coordinate system, if you move around, you should be moving on a sphere, not on a little box like Cartesian, not on a beer can like Planet Schlitz. You won't be on a cylinder. You should be on a sphere. So the way we do it is the same. We start out at the origin, and we point out the x-axis, right? But there's one big difference, okay? You actually start by looking straight up, all right? And then you still need 3 pieces of information. To get to the projector, I need to know the angle of the turn. That's still theta, okay? Then I need another angle, which is going to be phi. And it's going to be the angle from directly up the z-axis down to the projector. So So theta, phi, and then how far to walk out, which we call rho. So you don't confuse it with r. R is what we use for polar. So let me show you the picture here. I think my animation does a decent job of this. Make it a little bigger. So we're trying to move around. We have some, this is our x-axis. We rotate by some angle, theta. We come off the z-axis some angle, phi. And then we walk out from the origin to some point, and that's our rho. So if I were to start swinging theta around, it would almost look like I live on planet Schlitz, right? Wouldn't that, if I hold rho and I hold phi constant, then it's going to draw a little circle like this, which almost makes you think we're on planet Schlitz. It's when I hold theta constant and I hold rho constant and let phi change, look what happens. It's not going straight up and down. It's actually going through an arc like this, like that. And so if we put it all together, and you think about all the different possibilities, then I need to change my phi here. Get my phi down there. Okay, you see that? Your phi is going to give you some arc this way, and then your theta gives you a circle, and then your rho just changes in and out, so you get like a ball, solid ball. So you got planet ball. Okay? That's all it is. It's a ball. It's not as fun as a can. There are some restrictions here, though. Theta must be between 0 and 2 pi. So when you start pointing out the x-axis, you're looking up, theta has to be between 0 and 2 pi. So you can only go around one full revolution. What about phi? Its restriction, this is 0. So what would the restriction be? There's pi, this is pi over 2, and then pi. You do not want to come back around. You'll be drawing it twice. So your phi restriction is between 0 and pi. I'm going to have all this up on the board here. Did I have a little zoom in here? What is this thing? Oh, just zooms it in. What is this? Oh, that shows, oh, cool. I forgot I had that on there. That shows a little region, a little slice. So if you had like a little infinitesimal change in theta, change in phi, change in rho, it would draw you that little patch. That's a spherical little patch, three-dimensional. Cool. All right, so here are all the restrictions. Now, do you remember when we do polar, you have to convert? So x was r theta, y was r, sorry, x was r cosine theta, y was r sine theta, right? Z stayed z. Well, when you do Cartesian to spherical, the conversions are pretty wacky looking. They aren't the same as polar. They aren't the same as cylindrical. They are these. All your x's will be converted to rho cosine theta sine phi. Phi or phi, you can call it either one. I've heard it both ways. Phi or phi. How many of you phi? 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 Okay, I don't care. I say both. Rho, so every time we see an x, we replace it with rho cosine theta sine phi. Y is replaced with rho sine theta sine phi. And z is replaced with rho cosine phi. Phi phi pho. Now, we do have kind of like a Pythagorean identity here. X squared plus y squared plus z squared is rho squared. Theta is between 0 and 2 pi. And phi is between 0 and pi. And rho, of course, has to be greater than or equal to 0. Rho is the distance we walk out. There's your spherical coordinates. Now, why are spherical coordinates useful? We live on a sphere, right? I mean, we live on a sphere, roughly. So this coordinate system is perfectly suited for where we live. What is this?
It's like a slice of the
Looks like I did another one of those slices just to have fun. Oh, okay. No. I know what this is. We know what a box looks like. Remember we were talking about boxes in Cartesian versus polar? What does a polar rectangle look like? What does a Cartesian rectangle look like? Right? So if you were to do in Cartesian in 3D, if your x's are between constants, I'm just going to say constants here. If your y's are between constants and your z's are between constants. If x, y, and z's are all between constants, what's that going to draw? Just some sort of boxy looking thing, right? X's are between constants, y's between constants, z's between constants. You get that, right? What would in 3D cylindrical that look like? Cylindrical. So your x, we're in cylindrical. Theta's between two constants, r's between two constants, and your z is between two constants. What would that look like? Well, what does theta and r between two constants look like? It's a polar rectangle, isn't it? That's a polar rectangle. And then z between two constants means that it just has a top cap and a bottom cap. So wouldn't it look something like this? Something like that. On the top, it looks like a little polar patch on top, a little polar rectangle on the bottom, and then everything in between. So in 3D, this is a Cartesian box. All variables between two constants. In cylindrical, this is a cylindrical box. And in spherical, this is a spherical box. Because your theta's between two constants. Your theta's between two constants right here. Your phi is between two constants. And your radius is between two constants. And you can see on the back edge of this thing, it's got a little concave cutout section here. So it's scooped out there. It's not flat. This is what a box looks like, a rectangular box looks like in spherical coordinates. This is a box in Cartesian. It's the traditional box. That's a spherical box. All right, so if we want to convert and do a triple integral, so if we ever have a problem where we'd like to go to spherical coordinates, well, things are pretty good, I think. I don't know. Things are pretty good. Our theta's between two constants. Our phi is between two constants. Our rho's between two constants. So if we have one of these nice boxes, then we just go from alpha to beta, from C to D, from A to B. So there are all the restrictions. And then all we have to do is go into our function, replace x with this. Remember, every time we see x, we have to replace it with this thing. Replace y with this. Replace z with this. And here's the part that is kind of the catch, I guess you could say. The catch is that, remember in cylindrical, we always had to put an r? When you go to spherical, don't forget to put the rho squared sine phi. Rho squared sine phi has to be there. So it's a little bit more when you go from Cartesian to spherical than you go from Cartesian to cylindrical, right? Cylindrical, you just have to remember to put an r here. Spherical, rho squared sine phi. And I bet maybe some of you are asking, like, where did the r come from? Why do we have to do this? Well, that's the next section. The next section, we're going to show where this actually comes from. For now, just leave it as it is. Remember it. All right. All right. Let's first appreciate the scope of this problem, just how difficult this would be without spherical coordinates. We're trying to find the triple integral over E of the exponential function, e to the square root of x squared plus y squared plus z squared with respect to volume, where e is the region in the first octant between the spheres of radius 4 and 9. So you got a sphere radius 9, sphere radius 4. There's a region between those spheres in the first octant. You would like to take all those points in that sphere, plug them into this function, and basically sum it all up. You can't even project the shadow of that onto the ground because this does not qualify as your traditional surface on top, surface on bottom. Let me go back and try and explain why that is true. Go back to this region. Look at this right here. Try and rotate this so you can see it. Where is it? Okay, look at this. I'll look at this from the side here. If you were going to try and take this spherical box and cast a shadow onto the ground, number one, what would it look like? But do you even have a top surface and a bottom surface here? No. You don't. I mean, look, if I just draw a line, punch through, let's say I punch through right there, I'm going to come through and probably punch out right here, right? So the top surface would be maybe that lighter green. Yeah? Yes? But if I rotate this around and I go through and I punch through here like that, I would come out somewhere, right? But is this top surface the same as that other side was? They're not the same. This is a very complicated shape. And we can't do this complicated shape with your traditional cylindrical or Cartesian coordinates. We can't just say, oh, look at the shadow on the ground. In fact, there is no shadow on the ground. We're not even looking at the shadow. We're not even talking about a shadow on the ground at all. It's just that our theta is between two constants, our phi is between two constants, and our radius is between two constants. I hope that makes some sense. All right, so here's the region. If you weren't already on top of that, it's the region in the first octant between the spheres of radius 4 and 9. So there we go. Cooperate. So 4 to 9, sphere, outer sphere, inner sphere, and it's that region just in the first octant between those two. All right. Can you describe to me what this is in spherical coordinates? Like, can you give me some restrictions on things? Theta is between 0 and pi over 2. Good, because you're swinging, right, x-axis, y-axis. You're going to just swing in that first quadrant, so 0 to pi over 2. Phi goes from 0 to pi over 2 again, right? And then what about your radius, your rho?
The rho is from
4 to 9. So you have, this is a perfect spherical box, isn't it? It's a spherical box. So difficult to describe this object in Cartesian. Very difficult to describe what that is in Cartesian. You need multiple surfaces. It would be a disaster. Maybe even impossible to do. This, very simple. Now we're going to go set up the integral. And the important thing about the integral is we have to remember we replace x with a bunch of crap, right? It's stuff you have to remember. And then y is replaced with a bunch of crap. Z is replaced with a bunch of crap. And when we do the integral, we have to include rho squared sine phi, right? We have to include that. So let's rewrite this. Triple integral. I'm going to go from, let's go 0 to pi over 2. They're all constants, right? So order doesn't matter. 4 to 9. E to the what? Square root of?
It's rho squared
Yeah, isn't x squared plus y squared plus z squared rho squared? Yes? So this is just rho. You do the rho. Oh, rho. I have a cat. My best friend's wife, about 17 years ago, was like one of those cat lovers that like took a stray off the street, wound up being pregnant. The cat was pregnant, and the cat had like a bunch of kittens, right? And they already had like 3 dogs, birds in this little 1-bedroom apartment. They got all these little kittens everywhere, and so she begs me to take this cat, and I'm not a cat person, so I was like, all right, give me a cat. So I take a cat, and I look at it for the first day, and I'm like, go back to her. I'm like, give me another one.
Oh.
He needs someone to play with, right? I mean, I'm not. So got 2 cats, right? So what's that?
I'm not gonna play with you.
Yeah. Well, cats don't play with you anyway, but well, okay, they're not dogs. All right, so I got these 2 cats, right? That was in 2000. 2000. It was 2000. Okay. So the first cat that I got, his name is Rho. Okay. And the other one's name is Theta, right? Rho and Theta are my 2 cats. So Theta died 2 years ago, 3 years ago. Rho just won't die. He just, I mean, not that I want him to die, but he just won't die. He's an outdoor cat, and he just, we've moved 3 times, 4 times, and he just, every time he comes, lives outside, he's a perfectly good cat. Anyway, I'm thinking about him right now. I wonder if he's still alive. He's, what, 18 years old? I mean, almost 18 years old. That's an old cat, man.
Yeah.
For living outdoor and only being, he went to the vet 1 time.
Oh,
He's only been to the vet 1 time in his life.
he's older than your daughter.
Oh, yeah. Oh, yeah. 18-year-old cat. Rho. Good old Rho. So whatever they tell you about take your animals to the vet and get all these things, no, just don't take them to the vet. They'll develop their own immune system. They'll be fine. All right, sorry. Rho. I couldn't help it.
You need a rho squared sine phi.
So I need a rho squared sine phi. My phis aren't very good. My phis look like empty sets. That's like the empty set, but okay, doesn't matter. However you want to do it. So I need that, right? Because I'm doing spherical coordinates, right? I have to have this because it's spherical. And then d rho, d phi, and then d theta. There we go. If I integrate that with respect to rho, I've got e to the rho squared. Integration by parts. I'm going to have to knock that power on rho down twice. So it's going to be 2 iterations of integration by parts to do that. And then from there, it should be pretty straightforward. Integrating sine phi and... Okay?
Sure.
That'd be it. Or you could have the computer do it.
On the test?
Yeah.
No, I mean, if you just wanted a quick answer.
I'm pretty sure this is being just set it up.
On an in-class test, it'll be set up. But on your homework or the mini exams, you need to work them all the way through. All right, so the answer, oh, I didn't get a decimal answer. One example.
One example, 3 problems.
Look at that. We got through 12-7.
We're not gonna have a couple homework for.
You got to do your homework, I know the homework kind of caught up to some of y'all on the in-class test because, you got to do the homework to the point that you're comfortable with it so that if I present you with a problem that's maybe a little bit more challenging, you'll be there. If all you're doing is take-home mini exams, that's all you're doing, like the final's not going to be pretty. So do this homework. Ask for help. Have a good day. Anybody want a cat?
I just lost
Anybody
mine,
want to
so-
take a cat? Care for this? He's a great cat.
Yeah, mine was an